Yes,
Um,
so we'll come to the second part of Andy Hart's talk. Please go ahead.
okay. So that, okay, once again, I'm having trouble sharing. Okay, is that visible now? Oh, is that visible, the part two?
Yes.
Yes.
Okay,
Yes.
great.
Yep.
Yeah, sorry about the technical issues. Okay, so for part two, I'm going to delve in a little bit more to the way to prove these things and related ideas. So the main formula that we're looking at here is the famous Billy-Jokish-Stanley formula, all the way back in '93. And so their formula, it was the first monomial expansion of Schubert polynomials. Did that? Can you still see my screen?
I see the Sage prompt again now.
Oh no.
Here we go.
Okay, excellent. Let's hope that doesn't happen another time. Okay, so their formula gave a monomial expansion of Schubert polynomials in terms of what they are called compatible sequences. And so there's they wrote Schubert polynomials as a sum over what would eventually be known as slide polynomials. And so the next step is in 2016, Asaf and Searles explicitly defined and studied systematically these slide polynomials. Then in 2018, Lamley and Shimozono introduced the backstable perspective into the literature, and they proved for their backstable Schubert polynomials, they proved an analog to the Billy-Jokish-Stanley formula. And then in 2023, Nadeau and Tawari defined and studied backstable slide polynomials in the context of studying their forest polynomials. And so I just want to mention that all of the basic definitions and results for compatible sequences and slide polynomials hold in our slightly more general setting where we replace integer words or compositions with what we're going to call colored words. And we use kind of three tools. And we'll talk mostly about the first one and a little bit about the second one. The first tool is what we'll call the colored shuffle algebra, which is just an algebra involving certain words. And this algebra has subquotients that are isomorphic to certain rings of backstable functions of which the Schuberts and slides form bases. And then the second tool is certain differential operators that act on this algebra. And the third tool that we're probably not going to really talk about is the idea of increasing suffixes of reduced words. Okay, so let's dive in. Well, we're going to start by letting capital A be a set with number one, a map, we'll call the value map from A to the integers, and number two, a total ordering that is compatible with the value map. So in other words, if value of A is less than value of B, then A is less than B. The only thing that we decide with the total ordering is what happens when they have the same value. So two examples, and these are essentially the only examples that we'll ever use. Number one is the integers with the value just being the integer itself and then the usual inequality. And then the second one is the set of colored integers. We'll call it Z bar. And it's just the set of all integers, A, where I give it a color C. So A is any integer. C, we're going to say, is a positive integer. The value of a colored integer is just the integer at the bottom. And the inequality is just that if you look first at the values, and then next you look at the colors. So you sort first by A and B, then you sort by C and D. And the integers live inside the colored integers in the simple way of just sending any integer A to A of color 1. So that's our definition. And then the set of words is just the, we'll call it A star to, from computer science. And This is just the set of all finite sequences of elements of A1 through AK, and we'll write it without punctuation. And then a compatible sequence, if I have a word from A star, a compatible sequence is a 2-row array where the word itself is on the top row. And then on the bottom row, we have a word of the same length of integers such that the bottom row is, number one, weakly increasing. Number two, well, if P was just integers, then I would just say BI is less than PI. That's the usual definition. So in this case, we'll just say BI is less than or equal to the value of PI, ignoring the color. And the third condition is that if there's an increase in P, then there's got to be an increase in B at exactly the same point. Okay, so let's let C of P be the set of compatible sequences for P. And let's take the subset C plus of P to be the set of compatible sequences where every entry on the bottom row is a positive integer. And so this definition by Asaf and Searles in the ordinary case, Nadeau and Tewari in the backstable case, is that the slide polynomial is given by this formula. So F sub P is the sum over all positive compatible sequences. And we just take the monomial where you write X, if the bottom row is B1 through BK, we just take those variables, X sub B1 times X sub B2 all the way up to X sub BK. And the backstable slide polynomial is exactly the same definition, except instead of just positive compatible sequences, we now use all of them. These are not strictly speaking polynomials, but we abuse terminology as is convention. Okay. And so there are a lot of simple facts you can say about these polynomials in this combinatorics. For one thing, the set of all bottom rows for any word P has a maximal element, we'll call it M of P, under entry-wise comparison. So this is under weak inequalities in every entry. We'll see an example in a moment. A second thing is, well, M of P is a bottom row, and the bottom rows are always increasing word or weakly increasing words of integers. So this is some weakly increasing word of integers. And furthermore, if I take that, because this is now a word as well, if I take the maximal bottom row of something that's already a weakly increasing word of integers, I just get the same thing back. And so then in particular, because the slides and backstable slides are defined as sums of compatible sequences, the slide polynomial for P is equal to the slide polynomial for its maximal bottom row. And the same thing is true for the backstable slides. And so we can look then at just the slide polynomials where they're indexed by weakly increasing sequences of integers. And so Asaf and Searles in the ordinary case, Nadeau and Tewari in the backstable case showed that these sets of slides or backstable slides form bases of important rings. So in the case of ordinary slides, it's a basis of this polynomial ring in x1, x2, etc. And in the case of backstable slides, it's a basis of the ring of what are called back quasi-symmetric functions, which we'll say a little bit more about later. So here's a quick example. Let's let P be the word 212. And so this is in Z star, right? It's a word of integers. But I also want you to think of this as a reduced word for the longest permutation in the symmetric group on 3 letters, okay? It's not necessary for this example, but that's the context in which we'll use this. So then the set of compatible sequences for P is just this list. It's an infinite list because you can have you can have very negative integers in the bottom row. And so it's all these bottom rows that satisfy the inequalities for compatible sequences. And so notice that the maximal bottom row is this one, 1, 1, 2, because if you look at all the other bottom rows, none of them has a first integer larger than 1, none of them has a second integer larger than 1, and none of them has a third integer larger than 2. And if I look just at the positive compatible sequences, you can see that this is actually the only one because everything else has either a 0 or a negative number in it. And so putting this all together, what this says is the slide polynomial for this word 121 is just, when I'm talking slide, I'm looking at just positive compatible sequences. So I do x1 times x2. That's my only monomial, it's this. And the backstable one, I do the same thing, but I'm summing over all compatible sequences. So I get the same monomial. Then from this compatible sequence, I get that monomial. From this compatible sequence, I get that monomial, and so on. Let's do another example. Let's do the other reduced word for the same permutation, 1, 2, 1. That's again in Z star. And the set of compatible sequences is listed here. And the thing that's interesting here is actually none of these compatible sequences are positive. So the ordinary slide polynomial, even though P just involves positive integers, the ordinary slide polynomial for P121 is in fact 0. The backstable slide polynomial is definitely not 0. It's in fact, again, this infinite sum of monomials here corresponding to the compatible sequences. Okay, so our third example, we'll go into Z bar star words in colored integers. And here are the compatible sequences. Notice that the bottom rows of all of these compatible sequences are exactly the same as this one. Okay, so the maximal bottom row in particular of P is the same as it is for 1, 2, 1. It's 0, 1, 1. And so the backstable slide polynomial of any word is the same as the slide for its maximal bottom row. And so in both cases, this slide equals this, the maximal bottom row. This slide also equals the same one. And so these two things are equal. Now let's talk a little bit about the Billy-Jockish-Stanley formula. So first of all, for any permutation, S sub Z just means it's a permutation of Z moving finitely many elements. Let Rw of W be the set of reduced words for W in the Coxeter sense. And the Billy-Jockish-Stanley formula, done in the backstable case by Lamley and Shimozono, is that the Schubert polynomial is a sum over all of the reduced words of the fundamental slide polynomials. And similarly, the backstable Schubert is a sum over that same set of reduced words, but it's the backstable fundamental slides. And like I mentioned earlier, the Billy-Jockish-Stanley formula comes far before the explicit definition of slides. And so they wrote this as a particular sum. They didn't use that terminology, but that function does appear in their work. Okay, and so we want to multiply Schuberts, and so it makes sense to try to multiply slides. And luckily, the slide multiplication is far, far easier than Schubert multiplication. So the slide polynomials multiply according to a modified version of the Eilenberg-MacLane shuffle product. So the shuffle product is a little hard to explain. Basically, a shuffle of two words, P and Q, is just an order preserving interleaving of P and Q. You can interleave it however you want, but the order of the elements coming from P and the elements coming from Q has to be preserved. So it's best to look at an example. If I have P as the word 1, 2, Q is the word 3, 4, I have to keep the 1 and 2 in order, and I have to keep the 3 and 4 in order, but I can put them in any order relative to each other. I can put the 1 and 2 first, I can put the 3 and 4 first, or I can interleave them. And let's let the shuffle product P and Q be the sum of all shuffles of P and Q. So now we're working over the vector space with basis A star. And then we have the colored shuffle product. So now I have two words that are going to live in Z bar star. So these are words of colored integers. And we're going to define P times Q to just be the sum of all shuffles of P and Q, where the colors of Q are shifted to be larger than those of P. Okay, it just sort of keeps track of which integers came from P and which came from Q. So here's a quick example. If I have two words, and we'll think of these as being just words of integers because they all have color 1. So I have color 1 here, color 1 there, but when I do the product, I shift the colors of this word up far enough so that it's larger than the colors here. So in other words, I shift this to color 2. And when I do so, then I have this one integer of color 2, 2, 2, 2, and 2, and that can be anywhere that can be put in any place of the other three integers. And so this product turns out to be associative, but as you can see from this example, it's not commutative, right? I have here 3 entries of color 1, 1 entry of color 2. If I did the reverse order of the product, I would have 3 entries of color 2, 1 entry of color 1. And this does matter because compatible sequences depend on the relative ordering of entries. And so they do depend on exactly how you take this product. Okay, and so we're going to call the resulting algebra the colored shuffle algebra, capital Q. Okay, so it's the set of words in Z bar star with the sum being formal and the vector space spanned by that, with sum being formal and product being this colored shuffle product. So here's a proposition. This, in the case of ordinary words, was done by Asaf and Searles in the ordinary case, and Nadeau and Tawari in the backstable case. And in the case of the colored shuffle algebra, we just say for any P and Q in that algebra, the fundamental slide polynomial of the product equals the product of the fundamental slide polynomials. And the same thing is true for the backstable ones. Notice that this colored shuffle product is positive, and so this is a positive formula for the product of slides or backstable slides. Next up, let's define an equivalence relation to be that 2 elements of the colored shuffle algebra are equivalent if and only if they have the same maximal bottom row. I guess this would be equivalence for basis vectors and then extend by linearity. So in other words, for any elements of Q, P is equivalent to Q if and only if their backstable slide polynomials are the same. Okay, so this is a lot of sort of conventions and formalism, but here's the upshot of it. Let's take these 2 rings of functions. So R back is the ring of back symmetric functions. And I'm not going to give a formal definition, but essentially this means that if you go back enough in variables, then it ends up being symmetric in x sub k minus 1, x sub k minus 2, etc. And Q back is the ring of back quasi-symmetric functions. And these end up being functions that if you go back far enough are quasi-symmetric, so invariant under shifts of the variables, like shift from one variable to a different one. Okay, and so the corollary of all this formalism is that the colored shuffle algebra modulo equivalence is isomorphic to the ring of back quasi-symmetric functions just by the map of sending a colored word to its corresponding backstable slide polynomial. And then furthermore, let's let capital R be the subalgebra of Q generated by the following vectors. These are, we'll call the Schubert vectors, because it's just the sum of all of the reduced words of the permutation. And then it turns out that the quotient by equivalence of R is isomorphic to the ring of back symmetric functions via the same map where I send everything to its slide polynomial. And in fact, by the BJS formula, the Schubert vector is mapped to the backstable Schubert polynomial. Okay, so what this allows us to do is work with this sort of combinatorial, sort of lifted version of the backstable Schubert product. Now we're only working up to equivalence, meaning that the maximal bottom rows are the same. But now instead of the usual Schubert product, I can take this Schubert product involving the colored words, and then on the right-hand side, I have the same, the expansion of the Schubert product in terms of the Schubert vectors, which are reduced words. And so when I expand both sides by definition, I get some for every reduced word of U and reduced word of V and every shuffle of U and V. So this is going to be a word with 2 colors. And then on the right-hand side, I have a sum over reduced words of W, and I just have this reduced word here. So it's a 1-color word. And so what this means is that there's a multiplicity preserving correspondence, but otherwise bijective correspondence between the shuffled words on the left and the reduced words on the right. And this correspondence preserves bottom row equivalence. So let's see an example, because I know this is getting a little technical. But so here's our example. We're doing the Schubert product of S1 and S1. And so we know what that is by Monk's rule. But I'm going to do it with the Schubert vector. So the Schubert vector of this thing, if I do the left-hand side, I take the words and I do the colored shuffle product, I end up getting these as I end up expanding this product as 1 bar plus 1 bar 1. And then I want to take the maximal bottom row of both of these words, and it turns out that it's these things. And from here, my goal is to find out a way to write these as equivalent to some sum of Schubert vectors. So in particular, let's say I notice that 1, 1 is the maximal bottom row of the word 3, 1, right? The maximal bottom row here would just be 1, 1. And so I'm like, okay, maybe 3, 1, well, S3, S1, that's a reduced word for the permutation S3, S1. What if that is in my Schubert expansion? Well, if that were the case, then I would also have the word 1, 3, and that has maximal bottom row 1, 3 that doesn't appear here. So that one actually isn't in the expansion. But instead, if I use 2, 1, that has the same bottom row 1, 1, but that in fact is the only reduced word for its permutation. And so that's how I can figure out that this comes from the permutation S2, S1. And by similar methods, I can conclude that this permutation here comes from, or this row here comes from the permutation S0, S1. And so we have now the Schubert expansion, technically the backstable Schubert expansion of Schubert sub S1 squared. If you want the ordinary, again, you just get rid of anything that has a 0 or below. Okay. So this is clearly, like, if you could do this infinitely well, you could solve the Schubert problem this way, because there's only one way to group these things into Schubert polynomials, into Schubert vectors, and that is the correct answer. Okay, but it's a hard problem, obviously. The fact that we can do it for small cases doesn't mean we can solve the Schubert problem. That said, it does end up being useful to understand combinatorial properties of this product. So this was kind of our method of proof for the back stabilization formula. It's along these lines, kind of using Coxeter theoretic properties of increasing suffixes of reduced words, because the suffix of a word tells you something about the compatible sequences in the maximal bottom row. Okay, so the last thing I want to say, because I know we're running short on time, is I want to talk about the other tool that we used, which are these differential operators. So these differential operators, so Stanley defined in his shenanigans paper this differential operator nabla. It's not the same as McDonald nabla, but nabla has the form, so he defined it on Schubert polynomials, and then Neneshev extended this definition to backstable Schuberts and defined an operator xi on backstable Schuberts. Okay, xi only lives on the backstable functions, not on ordinary non-backstable functions, but nabla lives on both. And so nabla can be written as a differential operator, but I've written it combinatorially. So we just kind of divide on the left by any left descent S sub k. And then we multiply, in the case of nabla, by k. For xi, we do exactly the same thing, except we don't multiply by k. And xi actually can be extended from the ring of back symmetric functions to the ring of back quasi-symmetric functions. And these operators, as Stanley and Neneshev proved, satisfy the Leibniz rule. Okay, so we're going to do a definition where we're instead acting on the colored shuffle algebra. And these are similar definitions. So if for xi, what I do is I have some word, and all I do is I chop off the first entry. That's kind of analogous to left dividing by S sub k. And for nabla, I do almost the same thing, except I multiply by the value of p sub 1. So remember, that's if I have a colored integer, it's just the integer part of that. And so that's kind of analogous to left dividing by S sub k and then multiplying by k. And these operators also satisfy the Leibniz rule. And so here's our theorem. So both of these operators preserve the subalgebra generated by the Schubert vectors. I should mention, when I say the subalgebra, I mean you can do sums and products. So this involves all these kind of fancy colored words that you get by multiplying together Schubert vectors. And furthermore, the following diagrams commute. So if I apply nabla to R and then apply, then go, this is when you go to the slide polynomial. So apply nabla, you go to the slide polynomial. It's the same as going to the slide polynomial and then applying Stanley's nabla. And similarly for Xi, except for Xi, it works on all of Q, not just on R. Okay, so in particular, this is saying that, so let's look at nabla again. Here, that if I have two elements of R that are bottom row equivalent, then that means they're going to map to the same element here. And so they're going to map to the same element here. And so they need to map to the same element going around the other way, which means that they have to be bottom row equivalent there. And so the conclusion here is that if I start with bottom row equivalent elements here, then I end up with bottom row equivalent elements here. This does not work for nabla and the entire colored shuffle algebra, only this subalgebra R. Okay, and so I know this can be a little bit abstract, but this result is the main tool, and I'll do a sort of very basic sort of example to get some of the feel of it as the last thing. It's sort of the main tool to prove the no gaps part of Lee's conjecture, and also to go between ordinary and backstable structure constants. So one can use it to sort of kill off permutations with simple reflections out of the desired range. For instance, if you're not sure, you know that a certain structure constant maybe appears, but you don't know if it's an ordinary structure constant or just a backstable one, you can apply these operators to get rid of it. So let's do a quick example. It's a very basic example, so it only gives a flavor of this. But let's take Schubert S1 times Schubert S1, and let's apply nabla to that. And so this is when I expand this product, I get 1 bar plus 1 bar 1. So I apply nabla to both of those. And remember what nabla does is it truncates the first letter and multiplies by the value of that. So in this case, the first letters are 1 and 1 bar. And so I just get 1 bar plus 1. And if I look at the maximal bottom row, these both have the same maximal bottom row, which is just a 1. And so in particular, I get this to be equivalent to twice the Schubert vector for S1. Now let's do the other side of the Schubert product. So when we did this example a few minutes ago, we saw that the Schubert product of S1 and S1, or the backstable Schubert product, was equal to the Schubert for S0 S1 plus the Schubert for S2 S1. And so let's apply nabla to that side of the equation. And so when we do this, we get nabla of 0, 1 plus nabla of 2, 1. And so what it does is it chops off the first letter and multiplies by that value. And so when I do that with 0, it kills it, right? We get 0 times 1. And then we add 2 times the last entry here. And so we do get the same value. But notice that this word didn't contribute at all. And so in particular, the fact that I can get something over here that, and by applying nabla, means that I had to have something over here that doesn't start with a 0. So this is an obvious conclusion in this case, because otherwise the Schubert product would be trivial here. But it's the case that not every W where the backstable structure constant here is non-zero has a left descent at 0. Again, that's trivial in this case, but there are other cases where it's a lot less obvious, where we can use the same tools. Okay, that's everything I've got. Thank you.
Let's thank Andy for a very nice talk.